Okay, so now let's look at sort of the other end of the spectrum. We've seen an inconsistent system where we have no solution, and now let's look at a dependent system where we have infinitely many solutions. So let's look at this matrix that we've been given. This matrix represents the reduced form of a system of equations, and so we would like to write the solution for this system using parameters. We have to use parameters when we write the solution to a system of equations that is a dependent system, simply because we need a way to be able to describe what types of points are going to be a solution to our system of equations. So the first thing we want to do is let's go ahead and write each of these equations that the rows give us. Let's go ahead and write them out. So the first thing that we have, let's determine our variables. Let's call them x1, x2, and x3. So the first row tells us that x1 plus 0x2, so we don't need to include that, plus x3 is equal to negative 3. The second row tells us that x2 minus 2x3 is equal to 4. So notice that we can solve for, we could solve for the variable x1, and we could solve for the variable x2 in terms of the variable x3. The other thing that's telling me that I can solve for x1 and for x2 is because the leading one is in the column that corresponds to x1, and there's also a leading one in the column that corresponds to x2. x3 does not have a leading one in its column, and so this is what we call a free variable. By having a free variable, that tells you that you want your parameter to represent that free variable, because that free variable is free to be whatever it wants, so it doesn't matter what number it is, and so we need to introduce a parameter to represent that variable. So let's see. If we take our first equation and solve for x1, we have x1 equals negative 3, equals negative 3 minus x3. And if we solve the second equation for x2, we have x2 equals 4 plus 2x3. And so now what we're going to do is we're going to introduce a parameter. A parameter is a new variable. We typically use things like h or k or s or t, so just a single letter, and it shouldn't be one of the variables that you already have in your system. And so we're going to say, we're going to use k for this example, so let's let k equal our free variable, x3. So now we can write our solution. x1 has to be negative 3 minus k, and x2 has to be 4 plus 2k. This is what we call writing our solution in parametric form. Typically, though, we will write it in parametric form as a coordinate point. So writing this as a coordinate point, my x1 value is negative 3 minus k. The x2 value is 4 plus 2k. And the x3 value is just k. And so we would indicate our final solution as this coordinate pair where we see that x3 can be any value and x1 and x2 are dependent on the value of x3. And we've indicated all of this with the parameter k. So now let's go ahead and do a quick summary. We've seen that we can determine if a system of equations has no solution, and that's what we call an inconsistent system. This occurs if we have a row of all zeros in the coefficient side of the matrix, but a non-zero in the constant side. We've seen previously that a system can have a unique solution, and that would be if we're able to actually solve the system and get a solution for every variable. This happens when the number of non-zero rows in the reduced matrix equals the number of variables. So if we look at our previous example, our non-zero rows, we had 2 non-zero rows, but we had 3 variables. So that's why we don't have a unique solution. If our third row was a non-zero row, then we would have had a unique solution. And finally, we've seen that a system of equations can have infinitely many solutions if we have a dependent system. And this would be when the number of non-zero rows is less than the number of variables. And that's what we saw in this last example. We have 2 non-zero rows, but 3 variables. So the number of non-zero rows is less than the number of variables. So given any matrix representing a system of equations in reduced echelon form, you should be able to determine how many solutions that system of equations has just by looking at the matrix.